Good evening. On behalf of Engineers Australia, I'm delighted to welcome you all to tonight's Thought Leader series on segmental block retaining walls for infrastructure. My name is Megan Purdy and I'm the Corporate Engagement Manager here at Engineers Australia, and I will be your host for tonight. Firstly, in keeping with our tradition, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders past, present and emerging. Our webinar tonight will focus on segmental retaining wall systems, and our speakers will discuss the segmental retaining wall block product used in several major projects from Australia and around the world, with a focus on the design methodology and the engineering details used. Before we get started, I'd like to acknowledge that tonight's seminar is being hosted with our industry partner, Austral Masonry. Austral Masonry is one of Australia's largest manufacturers of concrete masonry blocks, retaining walls, pavers and stone products. Austral's innovative solutions can be seen on their high-end architectural projects and landscaping designs. Their commercial solutions include large-scale segmental block retaining wall products and permeable segmental block paving. Austral takes pride in its products, which are of the highest quality and are both durable and beautiful. Tonight's webinar, we're going to have two speakers present, and we will also then follow up with our Q&A session. So if you have any questions for our speakers, please send them in via the chat box, and we will remind you during the actual presentation of when you can start to actually load up your questions. Don't forget though, please include your name, where you're from and who your question is for. I would now like to welcome our first speaker, Daren Gardner, Managing Director at Keystone Hardscapes International. Daren specialises in segmental retaining wall systems and masonry solutions and has an extensive background in masonry services. Tonight, Daren will provide insights from over 25 years working around the world on major products using the Keystone retaining wall system, and will focus on the benefits of Keystone's positive pin connection, as well as alternate segmental retaining wall installation methods. Please join me in welcoming Daren Gardner.
Good evening, everyone. My name's Daren Gardner. I'm from Keystone International. I'm here today to talk to you about segmental retaining walls, and in particular, Keystone segmental retaining walls. I'm going to talk a little bit about our positive pin connection and then a bit on alternate segmental retaining wall installation methods. Segmental retaining walls come in many shapes and sizes. They really came into being about the late 1980s when some contractors in Minneapolis got together. They were wet casting some segmental retaining wall units and found out that they could use a dry cast method. The methods that are used today by manufacturers such as Austral Masonry on machines that they use to make pavers and blocks. So it was a more economical solution. From that point, Keystone started to develop the market, and we've spread out into over 30 different countries using the product extensively throughout the wall, as you can see here. Since then, there's been thousands of different faces and options for segmental retaining walls, and they're not always recognised as a Keystone face, but many times they are Keystone. So as I said, they come in many different shapes and sizes. You can see the top row here being our country manor. Then we have our sentry wall and the stronger unit down the bottom, the Keystone compact unit. But they all have similar features, being the pinholes on top. Each here, the recess for the Keystone pin, and this one has the kidney hole. Different face options, the Keystone unit on the left here being the hewn stone, the more natural look, or the triplanar face, or the straight face with a hard split option. When we originally made the unit, the first unit we manufactured was the one on the left here, the standard unit, or close to this. It's a deeper unit, and we made it deeper because we wanted to use it for gravity walls. And then, of course, when we developed the international market and we started to work with geogrid manufacturers, we realised a mechanically stabilised earth wall didn't need such a deep unit, and we come up with the Keystone Compact. This is the Compact 1. The unit on the right is the Compact 2. So again, it has the area for the drainage material, the pinholes for the front and back option, which allow us to build our wall near vertical or different setbacks, and the kidney holes that sit over the pin. When building or using Keystone segmental retaining walls in Australia, the blocks need to comply with the ASNZ standard 4455. This means that they need to have an unconfined compressive strength, a minimum of 12 MPa when using a segmental retaining wall unit on just a residential wall, low height or landscaping wall. Of course, there's also a highway code in Australia, such as New South Wales RTA's RMS's RTA code, or Vic Roads, Queensland's TMR code, and South Australia's DIPTI. When using the product in accordance with this code, you need a minimum unconfined compressive strength of 25 MPa. And then we may decide that we want to use the block for marine grade. So that would be a 30 MPa unit. And all the units have maximum moisture absorption rate of 8%. Leading up to the late 20th century, the face options for soil retaining walls were quite limited, and typically materials used were either the boulders or the timber sleepers, railroad ties, or the simple cantilever or counterfort walls. And these materials were used to build simple gravity walls, where they would use the material, the weight of the facing element, pushing down to resist the loads behind the wall up the top. Also, with a piling wall, we would have the element is keyed into the subgrade, and that piling wall uses the resisting forces on the front of the wall and the back of the wall to resist those upper forces and to stop any bending or overturning of the wall. Pardon me. Then, of course, we have a cantilever wall, which has an extended base at the back of the wall and has a toe in front of the wall, and it uses those same resisting forces to stabilise the wall. So you can notice these walls here don't use any mechanical elements to resist overturning or sliding, and depending on height, the methods can require a lot of material to stabilise the wall. So it's not always the most cost-effective solution. In the early 1990s, design methodologies based on well-understood earth pressures theories were developed, and they were tailored specifically for segmental retaining walls. They come up with these design methodologies are the Australian standard AS4678 or the British BS8006, the US AASHTO and the NCMA, of course. And these design methodologies basically all said the same, that in most cases, you don't require any structural footings for a segmental retaining wall, and you can use the on-site soils instead of any select granular backfill. Therefore, segmental retaining walls became economical solutions to create aesthetically pleasing sites. So building a simple gravity wall with a segmental retaining unit is quite simple. We look at the wall height, which is from the top of the wall to the base of the wall, and that includes any embedment. Of course, embedment requirements for Australian standards are 5% of the height of the wall, and they're different for other design methods. Behind the wall, we have drainage material, a 12 to 20 mil crushed sharp aggregate. This drainage zone extends from the face of the wall to the back of the drainage zone being 600 mil. And it's very important. It's important for a couple of reasons. Number one, if there is any water that gets behind the wall, it'll relieve any build-up of hydrostatic pressure, allowing the water to come through down into the Aggie pipe and out the front of the wall. And it also stops fine particles from migrating through to the face of the wall and staining the face of the wall. Our levelling pad here is just that, a levelling pad. It's not a footing. So segmental retaining walls don't normally require concrete or steel. It's just compacted gravel. And of course, we can use that depending on or relying on the fact that we have adequate bearing capacity under the wall. The bearing needs to be a minimum of 150 kilonewtons per square metre or 3,000 PSF. The materials behind the wall need to be compacted to 95% standard proctor density or 92% modified proctor. And we grade the wall so that we get the water away from the wall at all times, and using a low permeable soil cap on top of the wall. Of course, we need to build taller walls that take heavier loads, go much higher. So what we need to do is extend the base. And we do that by building a mechanically stabilised earth wall. And this is done through introducing some sort of reinforcing scheme. The reinforcing scheme here being geogrid. And we've extended the geogrid back using the soils behind the wall, compacting them and consolidating all that strength behind the wall to build one single mass gravity wall. Of course, all the other elements are the same. We still just need a compacted granular levelling pad. As long as we have adequate bearing capacity, we have the same 600 millimetre deep drainage zone with the same material and a cap on top. So at this point, with this consolidation of earth behind the wall, the facing units are there really just for durability, erosion control and aesthetics. As you can see in this design here, where we have a bank seat, which is sitting on top of the bridge abutment. This is a project in the UK. So we had to consider, the engineer had to consider the load from the bank seat. So he's used stronger grids, more grids and longer grids. The wall itself is about 6.6 metres high, whereas the grids are going back 7.7 metres because they applied safety factors. So all the strength is behind the wall in this area here in this consolidated zone. The facing element, again, is there just for erosion control and durability, and it stops a lot of this drainage material leaking out the front as well. Another bridge abutment, we've used Keystone extensively throughout the Middle East and Africa, a lot in Egypt, a lot of bridge abutments in Egypt here where they're using the same system. So it's common to see bank seats sitting straight on top of the abutment throughout the UK, but sometimes we also have pile casings behind the wall. In the case of the pile casing, though, we can work with that. This is a drawing from the Stadium Australia, built in 2000 for the Sydney Olympics, where they actually built 6 metre high Keystone retaining wall and built the stadium into that. So we had a lot of piles sitting behind the wall. We would use bodkin joints, which is a 3-inch galvanised pipe, galvanised steel bar joining another 3-inch galvanised pipe. So we'd wrap the grid around the face and continue it back behind the pile casing, or we'd just separate the grid to go around the pile casing. So there are ways around it. So, of course, on walls of much larger magnitude, we need to consider differential settlement. So these walls have an enormous amount of weight behind them. This wall in particular in Tonghua in China is the largest Keystone wall that I've been involved in, 45 metres high. It was built on 20 metres of fill. So you can imagine all that weight on top of the wall is pushing down, and because it's a corner, it's also pushing forward. So it was expected that the wall would settle and move. And in fact, it did. It settled 1.5 metres. So we needed to design for that and allow for that. And we did that by using construction joints and slip joints in the wall. But even after that, there was some cracking in the face of the wall. Generally, walls over 4.5 metres tall tend to crack more. Lower walls have lower confining pressures due to more facial flexibility. So when a wall is experiencing differential settlement, you see lower walls here will just tend to settle on their own and separate a little bit. Whereas with a higher wall, it has higher confining pressures, and you'll find that it will crack where the base is settling, where the foundation is settling. And you'll know that it's from differential settlement because that crack will extend in that area up the face of the wall. Different to when we experience lateral movement on corners. On a corner, when the wall would push forward, you'll find that you'll experience more random cracking on the wall. So that's how you can tell the difference between differential settlement and lateral movement. You'll also get gapping in the wall. So, of course, we can mitigate this in our design. How we can do that, walls up to about 6 metres high. We can use a simple construction method of using a control joint, cutting the face of the segmental retaining wall unit, leaving the back uncut and just stacking it as such. So when the wall does move, the back of the unit will crack and it helps the wall move naturally. On larger walls, such as this wall here with a railway line on top, heavier loads, we need to be very careful with differential settlement. We would do that by creating a control joint column. The column are 3 keystone units joined, mortared together, routed together, with the wings cut off the back and then stacked on top of each other to create a column. Each segment is then anchored into the reinforced zone behind the wall. And you can see the wall butts up behind this column, so this is where we can allow our differential settlement to happen in each of these panels. So anything over 6 metres high, you really need to consider your corners and consider differential settlement in your design because it can stop a lot of problems down the track. If we do get cracking with a segmental retaining wall system, they're quite easy to repair. For smaller walls, we can just take a wedge out of the wall, fix the problem behind the wall, being a floating boulder or whatever, and then just build that section back into place. I've had times where I've had to pull down walls, the face of the wall 6 metres high. You'll just see some of the drainage material will come out, but then we build the wall back into place because all the strength is in the consolidation of the material behind the wall. Of course, hard to do on taller walls. So what we can do is we can cut the face or jack out where the wall is cracked, cut the face off another unit and just epoxy it in place. Many benefits to the keystone pin connection. Segmental retaining walls come with different connection devices and types. Keystone's the only one with a pin. Most of them do have a lip on the back. But the keystone pin allows us to put our product in place and make sure that it stays in place after we put it there. We can manage a predetermined setback, so we can use a near vertical or a 4 degree or an 8 degree setback. We can pre-tension the grid by laying the grid over the pin, pulling it back into place. And by doing that, we utilise the full connection strength of the grid. So you can see here we have a lipped product and we have a keystone pin product. With the pin product, we lay the grid over the pin and we're able to pull it back nice and flat behind the wall and make sure we get that full frictional connection. Whereas with a lipped product, we lay the grid on top, there's nothing holding it in place. So as the contractors walk and work behind the wall, they can tend to displace units or displace the grid. So you always get full frictional connection with the pin system. The pin system also makes it much easier for us to work with corners. So in your design, it's best to design the walls near vertical, not with a setback, because it's also easier during construction. You can see this wall here. We can get a 900mm radius by cutting the back off the units, get a very tight radius, putting the pin in the front hole. Whereas if we're building, say, an external corner such as this one here, as the walls build up, they tend to bind. When they bind, you need to cut. It gets expensive. It can get messy. You can see some cuts on the units here. Tight corners, again, putting the pin in the front pinhole, such as here. All the pins in the front pinhole gives us a 1 degree setback or near vertical option. We don't have a vertical option because we still understand that people will walk behind the wall. During construction, the wall will move a little bit. So we want to stop that optical illusion of the wall looks like it's leaning forward. So we always start with a near vertical, not vertical. Of course, the pin in the back pinholes will give us an 8 degree setback. The back front will give us a 4 degree. And that's the difference you'll get in your corners. So this is much easier to work with. You can build these beautiful straight corners without any cutting. Easier for design, easier for construction. So you need to carefully consider grid placement when working on corners, particularly with higher walls, because with the higher walls, we don't just get differential settlement, we get lateral movement as well. On an external corner, you will see that the grids will tend to overlap. When grids do overlap, we need to make sure we've got a minimum 3 inches, 75mm between the grids. We don't want the grids touching each other and rubbing. We need to get the material in between, have it all locked into place and utilise that full strength. Also, on external corners, because we have these extra pressure on the corners, we'll increase the drainage zone. We do that by simple calculation, height of the wall divided by 2. We come back to a point on each side of the corner and then cross over, and that area will be full drainage material. Depending on the load on top of the wall, that could also be a no-fines concrete going into that corner. On internal corners, as the grids are laid back, they tend to separate. Once we reach 20 degrees of separation, we know we need to install another layer of grid. We'll do that by installing a grid on the next layer. So we just draw a line up the middle and then we throw a grid out there again, making sure that we've got a layer between each. So we've got that 200 mil between each and the grid is locked into that gravel. Not always easy to work out the embedment, particularly when we have a sloping toe in front of the wall. You can see the sloping toe here. So Australian standards require 5% of the wall height to be embedded. In this situation with the sloping toe, measure out from the face of the wall 1.2 metres. Where that intersects with the sloping toe, that's when we'll start our calculation of 5% of the wall height down from there. So that's our total embedment there. And what we've done is we've created a passive soil wedge in front of the wall. Of course, putting in our compacted road-based granular material, compacting it, and then putting our first layer in place. So our first layer, the wall will never be more level than the first layer. It's critical to get this layer correct, levelling each block left to right, front to back, because if we have any mistakes starting here, they're just exaggerated as we build the wall up, of course. So it's important to get that right. Once the units are down, we put our pins in place, we lay the block over the top, and another benefit of the pin is that we can drop this drainage material in around that pin, as you can see here. So doing that, it locks the block in with the face of the entire wall, so it becomes uniform with the wall. Some segmental retaining wall units, as you work behind the wall, they have freedom of movement, so they can pop forward or move back a little bit, and you've got to fix up the face of the wall later on down the track. But with this pin and the gravel around it, it locks it all into place. As I mentioned, proper grid placement is critical. When we do put the grid in place, we lock the grid over the pin and pull it back. And sometimes we'll extend that grid in front of the pin, make sure it's 40 mil from the face of the wall. The reason we do that is because that's how the grid is, the frictional connection strength is tested in the laboratory with the grid 40 mil from the face of the wall. Pull it back, pin it in place, drop some material on it, and in the fullness of time, the grid is stretched out and it starts to do its job. Materials of compaction behind the wall are placed. The drainage material, 600 mil from the face of the wall. And when we compact within a metre from the back of the wall with plate compactors, no heavy compaction equipment. Depending on your material and the moisture in the material, it's normally 6 or 7 passes with a plate compactor and you'll get 95% standard Proctor compaction. And drainage material is self-compacting. The next unit is then, the last unit is placed on top. The units are either pushed forward to the face or pulled forward to the face because gravity will take effect and pull them forward, drop the gravel in, lock it into place. If we find that the wall is starting to move out of alignment as we build up, we will shimmy the wall. And that means that we take a material that meets the design code by having the required life length, for instance, GeoGrid, 120 years. We'll pack that under the face of the wall to bring the wall back in alignment, making sure that we don't pack more than 2 or 3 mil at a time because you don't want to see that in the face as we do go up. So it's quite easy to bring them back into alignment. So that's grid. I spoke a lot about GeoGrid walls, but there are alternate installation methods, and one of them is our Keystone. The Keystone has been used extensively in New South Wales on highway projects, the UK, New Zealand, and quite a lot around the USA. And it's an inextensible hot-dipped, double-dipped galvanised steel ladder. The reason we would look at using steel is because as these walls get taller with higher loads, they do require a lot of grid. So depending on the price of steel at the time, it can become a cheaper option to use steel because you may only need one of these ladders every 3 blocks along and 2 courses high. So really one ladder every square metre, base square metre. So the steel are 9 up to 11 mil wire. They have crossbars. The distance of the crossbar is determined by the required pull-out length, pull-out requirements. It says here 75 to 100 year, but in Australia it's a 120 year design life. But they're a very good option to use. This is on the Waikato Expressway in New Zealand, last year installed, and we installed a number of those there. So they're a good mechanical connection to use when you feel that you're going to lose frictional connection, normally from wall movement displacement. Another great system that we have, and we designed in conjunction with Tensar, is the Keystone TW3. This uses both mechanical connection and frictional connection. So we still utilise the frictional connection of the grid to the block surface, but we get a mechanical connection by using the Tensar blue connector comb. This connector comb sits into a recess in the top of the block, but still using the Keystone pins for locating and other benefits, of course. The Keystone TW3 has been approved by the British Board of Agreement in the UK and has BBA certification as well for 120 years. So this is a project used in the UK just recently. You can see it's using the TW3. The majority of projects in the UK do use the Keystone TW3. Earth anchors are another option. This is a project in North Australia, North Queensland, where we had to create a usable space on top of the wall, but we had these trees in place already, so of course we didn't want to excavate and destroy the tree roots. So we come up with the system of using the earth anchors, where we would attach this earth anchor to the face of the block and push it in behind the tree roots. So there are a couple of ways to do this. Normally, with a segmental retaining wall, you would use a 3-inch galvanised pipe. It's attached to this cable, and then the anchor, a manta ray or a platypus anchor, in behind the wall. And then we would use a grid, which is wrapped around that pipe and back up on top of the block. However, with Keystone, because we have that pin system, the anchor can sit in the wall, the cable can come out and just wrap around that pin system, back onto itself, and we swage it, lock it into place, and just pour the drainage material in behind. So it's a very fast and very good system to use. Simple as the locations are identified by the engineer, a rod is pushed into place. If we don't hit any rock, we pull the rod out, put an anchor on the end, push that anchor back into place. The cable pulls the anchor parallel with the face of the wall, and that gives us our resistance. And it creates a frustum cone of resistance. This is a wall here that we pulled until it failed, so we can see that cone. This anchor was only in 800 mil, and it's pulled out this cone of earth. So the cables will hang out the front, wrap them around the pin, just pour the material in behind, and that's your finished product. It's also a great system if you need to build a retaining wall from top down, particularly in large, dangerous sites. You can build a top layer, excavate, build the next layer, excavate, build the next layer. No fines concrete is also a popular installation method. This method would be considered when we're really stuck for room. So you can see behind the wall here, they just need a little bit of no fines concrete behind the wall and more as the wall goes higher. So to work out how much no fines you need, we have a chart here that shows you maximum of 2.8 metres high that we recommend. And you work out the T-zone from the front to the back is half the height of the wall. So 2.8 metres high, we need 1.4 from the face of the wall. So you can get away in pretty tight areas. And it's a 10 MPa no fines concrete, which means it has no fine material. And what we're doing is actually creating a highly permeable block of concrete. Used in many parts of the world. This is a project in Sweden, so they like no fines concrete there because it's a quick installation method. Keystone's great in water applications, tidal, drawdown, wave action. Very good for wave action because there are a lot of openings, gaps in the blocks, so it allows the water to hit the face of the wall. The energy of the water is dissipated into the wall and the water can just draw out again. So very good for drawdown as well. So there are many applications for segmental retaining walls, but they're a flexible option when needing to manage grade change to create usable sites from difficult terrain. Segmental retaining walls are routinely used to facilitate development of sites that would not otherwise be possible. So thank you very much for your time, and I look forward to your questions after.
Thank you, Daren, for your presentation. I'd now like to welcome our second speaker, Namir Asmaro, Technical Systems Engineer at United Crib Block Construction. Namir has worked in the civil construction industry for the last 30 years, involved in project management, civil and structural design, construction, and solution-based technical sales. Tonight, Namir will be sharing his 20 years of practical experience in designing and construction of Keystone walls. Please welcome Namir Asmaro.
Welcome everyone. My name is Namir Asmaro. I'm the company engineer at United Crib Blocks Construction, UCBC. I'd like to share with you our experience in building Keystone retaining walls that we've gained for tens of years. Keystone walls offer many advantages. One of these advantages is the system being a one block system. So it's the same block that we use at the base course, the top course, along the wall, for walls that are 1 meter or walls that are 20 meter high. Keystone walls can also be built using different types of backfill materials. So in many cases, we've used the on-site materials, and once they are proven to be suitable to be used, which saved a lot of time and money for ourselves and our client. Keystone can also be built using different types of reinforcement. So the geogrid reinforcement that's available in the market, whether being HDPE, polyester, polypropylene, or also can use steel ladders for high loading walls, such as bridge abutments, quarry walls, and mining. There's also the use of no-fines concrete to create a mass gravity wall, and standard concrete and reinforcement, steel reinforcement as well. Keystone walls are easy to use to build around tight corners and curves. So whether it's the corner of 90 degrees, internal, external, the blocks can be adjusted, can be cut to suit these corners and create them with a very smooth finish, maintaining the connection in between these blocks. Keystone does not require heavy lifting machines such as cranes, because most of all these walls are actually built by hand in terms of block placement, and then the backfill material is done using the excavators or bobcats. Also, the Keystone is always available in stock, so you don't have to wait for a leading time for the blocks to be manufactured. They are off the shelf. You can start your wall with what's available in stock while the manufacturer, supplier, makes the rest. Just an idea, there's about 3,000 square meters that can be made a day of Keystone in the block plant. It's also available in different finishes, being straight face or a split face, and different colors depending on the manufacturer and the location. Keystone walls are also easy to construct, so you don't need an experienced, high experienced staff to do the installation. It's pretty much a straightforward, a repetition of the same step every course along the wall and the full height. The small block system also allows you to build your wall without having to sacrifice extra additional areas either at the base or at the top of the wall, especially if the wall has got many steps. And that's due to the actual small size of the block that we're using. In terms of applications, Keystone walls can be built in fill situation, which is about 70% of the cases where Keystone walls are built. And that's using the geogrids behind the wall to reinforce the soil and become a mass wall with the facing. The geogrid length is normally around the 70% of the wall height, depending on the loading, the soil parameters, and the geometry. But most of the times it is around that 70%, and it works perfectly in the fill situation. In other cases where you have a small room behind the wall, we use the no-fines concrete, which is a free draining material that bonds to the wall. We fill the core holes of the blocks as well as the back of the facing to form one mass concrete gravity wall, which does the retaining wall. It is in a cut situation where you have limited room behind it. Keystone walls can also be built as a double tier or triple tier walls, where in cases you have a high structure, high wall, and the architect wants to split that into 2 or 3 tiers and then have a landscaped area in between the 2 tiers. The design is also adjusted to suit and depending on this distance between the tiers, we allow for the loading, for the weight, and then for the height of these walls accordingly. One other method we've been using at United Crib is having the wall, Keystone wall, built on a 1-to-4 batter, which allows the no-fines concrete at the back to be trimmed to the minimum thickness, and that's where you have very limited room behind the Keystone wall where it's close to the boundary. It's been proven to be a very efficient and very good system to use in where you have a small room behind it. All the 4 cases that I've mentioned before, we use West Sydney, at Wetherill Park, where you can see the ones that I highlighted here, the 4 types of wall applications. We've used all using Keystone, same block, same finish, different approach, different design. The other wall I want to talk about is the project that we are currently building in Oakdale Industrial Subdivision, which is in Kemps Creek in West Sydney. This stage is part of the $3 billion Oakdale Industrial Estate. There is about 14,000 square meters of Keystone walls in total, and a number of 14 retaining wall structures. So an average of 1,000 square meters per wall. UCBC were awarded the design and construct contract for this project earlier this year, around March, April. And that's when we started doing all the design work, the preparation, procurement, and then the construction. Out of the 14 structures, we chose to talk about, showcase wall number 2, RW2, which has presented a lot of challenges to us so far and has been identified as the most challenging wall in this project that requires special attention in the design, supply and installation. So what are the challenges that we face with RW2? You can see the geometry of the wall were quite unique. It has about a 14-meter maximum height. It varies from chainage 0 to chainage 50, from 0 level up to 14 meters. So about 300 millimeter height, extra height every 1 linear meter in the first 50 meters. The soil properties we found also were quite challenging. The foundation soil was found to be soft and wouldn't meet the required bearing capacity of the 14-meter high wall. The retained soil was created by fill, so it's all a fill material, compacted, but still presented some sort of an uncertainty for us until we started building the wall. In addition, there's a 5-meter high sound wall or noise barrier at 1.8 meter behind the face of the wall. And that needed to be taken into account in terms of the design, allowance for any effect of wind loading, and that structure being right very close to the face of the wall. There's also a fence on top of the wall right behind the blocks, just 300 millimeter from the face. There's also a top 1 meter is or needs to be a geogrid free zone, which means that we couldn't place any geogrids to allow for future services to be installed at a later date after the wall is finished construction-wise. There was also an existing stormwater pipe in front of part of the wall that the wall was within the zone of influence of that stormwater pipe. It was about 5 meter deep and 3 meter horizontal offset. And we needed to do something to increase the depth or the embedment of the wall to go below that zone of influence. So this is our RW2. This is the elevation view of the wall. As I mentioned before, it starts from 0, goes up to the highest section, which is here, 14 meters within the first 50 meter in length. The wall length was 336 meters, and the total area was 1,800 square meters. The decision was made from UCBC management to use the Keystone TW3 system for this wall in particular. Given the challenges, the uncertainties, and the wall geometry, the height of 14 meters, we decided to use this system, which I will explain to you in a minute. So looking at the typical cross section, you can see how busy this section is. So it includes the wall facing, which is the TW3 Keystone blocks, the geogrids, which are placed on every 3rd block. And then you have all the other additional items. So you have the red geogrids here, which are pretty much used to stiffen or to support the pier of the sound wall, which is that 5 meter sound wall, both at the bottom and the top of the pier. We also have the no fines concrete, as mentioned, at the top 1 meter, where there's 2 layers of geogrids going into that no fines concrete to stiffen the no fines concrete even further, and then provide that support to any movement, or any effect of the sound wall pier, which is based right behind the no-fines concrete. In areas, we needed to extend the no-fines concrete from a 1 meter width to go to 1.8 to go right to the edge of the pier. And then the design called for a separation 100 millimeter of polystyrene foam between the two structures. You can also see the fence here. So we, UCBC, provided the sleeves for fence to be erected in the future. And pretty much everything that a civil and geotechnical engineer dreams of. The plan view of the top section here shows the wall. So these are the block, the TW3 Keystone blocks, showing the molded grid connectors marked here in rose color, pink, and the blue geogrid here is the grid that's based here in the no-fines concrete. The red color is the grids, or are the grids that are based at the bottom and the top to support the sound wall piers. As for the wall design itself, you can see the wall height here is the 14 meters. The grid lengths we calculated were around the 11 meters in length. And that was dictated by the global stability analysis that we've done, where the grid needed to be that 11 and a half meters. But you can see the loading here. It was 20 kPa loads, live loads, and 5 kPa dead load, as well as the top 1 meter, which was designed as an extra load or a slope, pretty much, to allow for the area that's not reinforced. And this is a closer illustration of the block and grid connections with the connectors marked in blue. With the soil, there were areas of the foundation soil, in particular at the highest part, where the bearing capacity was not nowhere near the required allowable bearing capacity. So the geotechnical engineer and the designers at UCBC worked out what is the allowable bearing capacity that's needed, and then the method was to excavate the soft soil right to the depth where the bearing capacity is reached, and then backfill the first 3 meters, which is 1.5 meter in front of the facing, 1.5 at the back, with stabilized cement, stabilized sub-base material, DGB, placed every 300 millimeter and compacted up to the level where the base of the wall starts. Same thing happened in the reinforced zone, where the bearing capacity of the soil was not meeting the allowable bearing capacity. So the material, the soil, then was excavated down to the good allowable bearing capacity value level, and then backfilled with sandstone granular material and compacted in a lift of 300 millimeters as well. During construction, this is the system that it was, for us, it was a system that we're using the first time. We had in mind that there might be delays or some complications in the construction. However, when we started building the wall, it was actually quite a smooth construction method, and we didn't have any difficulties in installing the system. You can see here, it's close look, this is the block, and there is the the pin connectors, and then the geogrid, which is the tensile geogrid, the HDPE grid that was used. And this system offers the best connection between the grid and the blocks, where you're guaranteed that the connection strength is right to the maximum, and therefore the grids are on every 3 blocks, and they are they give you a very good design in terms of the value, the construction, and the speed. In here also you see the blocks that are installed, and our team currently at this photo installing the blocks with the grids, and you can see there's nothing like unusual in terms of building a standard Keystone wall. This section here gives you an idea of the width of the grids, which is the 11 meters I mentioned before. And this is the facing, the sandstone backfill material. These are the geogrids, the tensile geogrids. And this is exactly the level where the bottom of the sound wall pier starts. And you can see the geogrids here are placed on an angle to allow for the piers to be inserted in here exactly. And this is the photo where it shows the grids and the blocks, the backfill materials, and this is clearly a low height wall right at the second half, which the wall is around the 3 meter high. When it came to the actual sound wall piers, we needed to use pier liners that were the 600 millimeter required by the design. So what we've done is we went up to a level where we actually used an auger to drill a 750 millimeter hole through the geogrids, through the sandstone, down to the required level, and then place the pier liner, and then concrete around it to fill in the gap, the 150 millimeter gap, and then align all these as you see here in the photo. So these are all the pier liners ready for actually completing the construction of the wall. Then we had the no fines concrete placed. This is the level where the no fines concrete starts. It's 1 meter design from the back of the block to here, to this point. And then we extended the no fines concrete further to go by the pier liners with the 100 millimeter polystyrene foam separating between the two. And here you can see the fence sleeves that we put in here for the posts to be inserted later. These are the liners when the wall is finished. You can see here the caps are installed, the geotextile that wraps around the no fines concrete, and then these are the pier liners here, 1.8 meter behind the wall, and this is pretty much the wall backfill material pretty much done. Give you an idea of the elevation of the wall. This is the wall RW2 when it's still halfway in height. So this is about 8 meters out of the 14 meter maximum height. And then the length of the wall, it's 335 linear meters, so quite a long wall. But it's been completed, I think yesterday or today will be done, will be finished. And another success story by United Crib Blocks Construction. Thank you very much.
Well, thank you, Namir. for your presentation. So now's the time where we get our speakers together and we get to hear from our audience. So if you do have any questions for our presenters, please don't hesitate to use the chat box to actually send your questions through. I can see we've had quite a few come through. We also have some questions that we've taken on registration, so we'll get to some of those as well. So to give Namir a bit of a break, I might start with Daren tonight. So the first question for Daren came from Subra in Victoria, and his question is, what is the maximum height of the Keystone wall constructed so far? Any issues?
Sorry, please continue.
Any issues when constructing that high, and what have been the remedies?
Okay, thank you for the question. It's funny, I get asked this question a lot. So the maximum height you saw in my presentation there was a wall which was 45 metres high, a Keystone wall, but you know, there's many walls around the world that are being constructed 40 metres, not just Keystone, but other segmental retaining walls. I think the highest wall originally we constructed was in Puerto Rico in Hacienda. That was back in the late 1990s, and we monitored movement on the wall to monitor displacement. After a period of 6 months, we only saw about ½ an inch of displacement. The system was still fairly new then. As I said, retaining walls were only, segmental retaining walls were only introduced around the late 1980s. So there's been many large walls since then. We tend to become more cautious with the walls once they're over about 6 metres high. That is a wall, a tall wall with a lot of weight behind it. So we like to get involved in the design if possible to make sure that we take all the factors into consideration. So some of the things we consider with tall walls are corners, so lateral movement in the corners, and differential settlement. So it's very important, and also, of course, external stability. I hope that answers your question.
Thank you. Namir, did you want to answer that question or anything to add?
No, I think Daren has answered the question quite well, so no addition. Thank you.
Perfect.
I will add to that, if you don't mind, that Namir was saying we do have a wall that they built at Oakdale, which is 14 metres high in Australia, supplied by Austral. There's another wall they're currently supplying in the south of Brisbane, and that'll be 15 metres high. So I think people are becoming more confident with design and construction. We're not seeing many problems with these tall walls as we understand them, so they are getting higher and higher. And really the limitation, I'd say, would be in the design.
Okay, thank you. I've got a question here. It came in on registration, and it's a really interesting question. It was set for both of you. Are there any robotic and or other automatic systems for constructing segmental block retaining walls? And that came from Paul in Queensland.
Namir, do you mind if I answer that?
Yeah, we're at UCBC are aware of these robotic systems around the world. We've actually been approached by a manufacturer to trial these robotic machines, but we still haven't gone to the stage where we are going to use them. Like practically, I personally believe that manual building these walls works better, as there are the difficulties of getting the robotic machines to sites, especially civil sites where there's a lot of difficulties there. And, you know, in terms of the actual placement of the blocks or even placing the machine itself around the wall. So I mean, it would I guess we'll wait and see what we find from the manufacturers of these robots.
Yeah, can I add to that as well, please? We do consider manual handling, because most segmental retaining walls units normally start around 30 kilograms, and they can get quite heavy. So with some systems, and I know with our system, we have bars called key lifters, So we design with these key lifters for 2 people to lift 1 block, so they can lift more for longer during the day, and it's not that dangerous. From there up, we do have systems such as a simple set system. It's basically a bar with some cables that hangs on the front of a loader, and that will lift 3 units at a time and place 3 units at a time. So as Namir said, the system that he's speaking about, it's like a gantry system where it has 2 sets of wheels and a gantry crane in the middle. The problem with that system, it is quick, but it depends on the geometry, the layout of the wall. So if you have a lot of, stepping, you have a lot of corners, it's hard to run the system. However, if you do have a large, long wall, it can work well. So there are systems out there.
Okay, thank you. Just off that, there was a question which came through from Ashley in Queensland. And the question was, best practice in deciding the geometry and loading for your retaining walls?
Yeah, can I answer this question? We as the contractors normally do the design and construct work, but we rely on what the client decides on in terms of the geometry or the loading. So I'm not sure I understand this question well, from the contractor point of view, we do what we're told to do pretty much. We can have our input to suggest other options, but these decisions are normally made by the designers of the client.
Fair enough. The next question that's come through tonight, and it's from friends from South Africa. Now his question is, do you have ASTM D6638 results for grids typically used in Australia? Do you see arching of the grid between pins? And I think this question's for you, Daren.
Okay. That's international standard testing results. That's something you'd need to talk to the grid manufacturer about. However, Keystone being an international system, one of the things we make sure we do is we take the latest units from our licensees around the world, the manufacturers, and we test them with the latest grids. Of course, there's some grids are more popular than others around the world, and at times it can depend on what's available in your country or local area. But we try to test as many grids with the units as possible and get a good understanding of the frictional connection. And then we use that data in our software program, which is available to everybody, and that will give you the latest connection data. So we do test that. And for that kind of standard, you'd need to talk to the grid manufacturer, but I'm sure they do have it. As for the arching on the grids, yes, we can experience that. And there are a couple of different types of grids out there. Of course, the PET and HDPE grids. It depends how you place the grid over the pin system. You can get arching when using grids with the larger transom bars, but you can always overcome that. And of course, we make sure that our grids do lay back nice and flat when they do go back. They're not up too high or down too low. So we try to keep them just flat as possible, just by hand.
Okay. Franz did actually have a couple more questions. The next one was around, does connection strength govern ultimate requirements for grid at specific depth? And he also then asked about why the limit of 2.8 metres on NFC.
Well, I can take the NFC if, Namir, you want to answer the connection strength.
Sure. All right. Well, connection strength is one design design check that we do when designing Keystone walls. It is related to, obviously, internal stability, and it can dictate the design. But normally, we find that the most influential factors are the external, the overturning and the sliding. These tend to be more dictating what the design ends as. The connection strength is important. Obviously, you want good connection strength between the grids and the blocks, but it's not. I haven't come across many cases where connection strength actually is the dictating factor.
Okay. As for the no fines concrete question, why is it limited to 2.8 metres high? That's because that's manufacturers' Keystone's recommendations. So when we put that engineering detail together, we had in mind who the majority of the users were. They were people that were building walls up to 3 metres high. So that's why it come in at that height. And also bearing in mind that no fines concrete can become an expensive option. Walls generally over 3 metres high, you're getting into larger structural walls or infrastructure, so they won't look at some sort of stabilising system like no fines concrete. They tend to look more at the grids or the ladders. So that was really where we limited it to. But in saying that, I have seen them higher, and I've seen them much deeper and used in conjunction with grid on the top. So it depends on the engineer at the time and what they're trying to achieve, but it is possible.
Thank you. We've got another question which has come through tonight, and that's from Shay in London. Her question, or his question, is how much movement can Keystone products accommodate, both horizontally and in terms of vertical settlement? I think it is.
Can I answer this question?
Yes.
We follow the Australian standard 4678, and there is a clause there that limits that movement, whether it's a vertical or horizontal, and that's for 0.004 of the wall height. So if you've got a 10-metre high wall, your allowable movement will be 40 millimetres. I hope this answers the question.
Thank you. We've got another question which has come through from Hassan in Melbourne, and his question is, can we use basalt strips for block retaining wall?
I'm sorry, I can't answer that one. I've never been involved with basalt strips.
He's asked that. He has actually directed that to you, Namir, but that's okay. I can jump onto another one.
I'm not sure I understand basalt strips. So are we talking the reinforcement or the backfill material? If it is, basalt is obviously a rock. So are we talking crushed basalt rock? If it is, then of course it is. Like it's a good granular material. As long as it meets the grading requirements and the compaction requirements, I don't see any problem with that. But if he's referring to something else that I can't understand, I'm sorry, I can't answer the question.
Sure, he may also be asking that, inquiring about the pH level in basalt and can we use that in retaining walls. I know that some engineers are concerned about the amount of pH and what effect that may have on HDPE grids or PET grids. So that is something to consider as well.
Okay.
Thank you. I've got another question which came in on registration, and it was probably for you, Namir. What are some cost-effective solutions for providing temporary retaining support to unstable slopes during construction of new permanent retaining walls? And that question came through from Timothy from New South Wales.
Thank you. When we build retaining the Keystone walls, the temporary batters are normally determined by the geotechnical engineers for the site before we start our works. So we know what we expect from the retained soil, how much, what a batter, what angle we can get, 1 to 2, 1 to 3, etc. So if we're talking about actually getting closer than that slope, which can present a high risk, there are some measures that we tend to do by either opening a limited length of the wall, building that section and reinforcing and backfilling, and then go to the next one so we don't expose bigger batter, retained soil, just for the maintaining the structure during construction. Other than that, we might require a redesign so we don't get too close to that cut, to the batter, and then limit the width of the reinforced zone, meaning using no-fines concrete or the likes as an alternative.
Excellent, thank you. We had another question come in from Alfie in Sydney, and it was about, in earthquake areas, does the frictional force between the blocks provide sufficient lateral resistance?
Yeah, when it comes to seismic or earthquake, that's always a tough one to address, because what is sufficient lateral movement? I mean, if we had a major earthquake, the wall's coming down and really no one cares about the wall. So when is it sufficient? That's when we need to look at the connection type. So as I showed you there, our Keystone TW3, it's become used quite a lot in New Zealand because of the seismic issues they have. They like the mechanical connection plus the frictional connection. But even without that, with that blue connector, the tensor connector comb, you still get that pin system. So you may get that sideward movement in seismic situations. You're going to get that location pin in there. Even when the product bounces up and down, you may get some aggregates come through the block, but the pin tends to still hold that in place. But how much can it handle? I mean, who knows?
Namir, did you want to?
Yeah, I actually come from New Zealand, and I spent many years designing and constructing walls in Auckland and even Christchurch. It is quite tricky how you design for seismic and what you allow for. Also, depending on the magnitude of the earthquake that you design for. But one reality is that we find that segmental blocks in general, Keystone in particular, have resisted really heavy earthquake events around the world. And that's due to the actual connection between the blocks that Daren mentioned. And even before the TW3 was introduced to the world market. So these walls have their flexibility around movement in earthquake events. And as I said, like, they performed really well in previous events.
Excellent, thank you. Namir, while I had you, I've got another question for yourself, and it was around, and this question's actually come from Hasib from New South Wales, so thank you, Hasib. What are your thoughts on designers specifying 5 kPa design surcharge for retaining walls in industrial subdivisions?
Yeah, again, I don't want to this is something that we don't get involved much as contractors, as wall designers and installers. We go with what the clients decide the design loading is. Normally, if it's up to us, we allow for a minimum of 10 kPa loading that we call construction loading. And that's for the diggers and bobcats on sites that are working right behind the wall or in the reinforced zone. We allow for that loading as a minimum. 5 kPa tends to be the loading where you only have landscaping area behind the wall, or no loading at all. So that 5 kPa becomes the minimum. Again, it really depends on the application and what's required.
Thank you. We've got a question which has come through from Jayantha through the chat box tonight. What are the main maintenance issues with these segmental block retaining walls?
Okay. Depends where you are. Of course, we have in some of our colder areas, they have freeze-thaw issues where they salt the road, and the salt can tend to corrode the face. That's really been the biggest problem with any segmental retaining wall unit. People do get concerned about the product in a marine environment As I said, the product works very well. And in fact, Keystone has invented a block which we use as a fish house, where we have an opening in the front of the block. We allow fish to swim in, lay eggs, so larger fish can't eat their eggs, and it increases the fish population in that area. And that's been quite popular in China for waterway rehabilitation. But the concrete works well. That's why we have a higher compressive strength, 30 MPa and higher, because we don't want that water to get in and out. So really the biggest problem we've had has been with freeze-thaw and the salting around the road. Other than that, when it comes to movement in the wall, we try to limit it to 10 millimetres in openings, any gaps in the face of the wall. We do that because we don't want the drainage material or smaller material coming through. But other than that would just be some slight vegetation and that sort of thing.
Excellent. Thanks, Daren. I have another question, and it is from Robert in Queensland. His question is, ability to install pedestrian safety fences at the top of the wall. How much setback is required, as more than 300 millimetre may create safety and design risk for maintenance staff?
Well, can I answer this? In about most of the walls that we built, we normally allow for fences to be installed hard against the block. So that's 300 millimetres from the face, or even sometimes through the core hole of the blocks, so right on top of the Keystone wall facing. Normally, the pedestrian footpaths would be placed around a metre or so behind the wall edge. I personally haven't come across any scenario where the footpath is right on the edge of the wall, especially if it's a high structure. But anyway, from the design point of view, there's no problem. From the safety, I guess it follows what the local council or the standards in that specific area.
Excellent. Thanks, Namir. I've got another question. Unfortunately, I don't have a name, but they've got two questions. So the first question, how far and deep is the exclusion zone if future services are laid too close to the wall? Is their first question. So if someone wanted to jump on that one. So just to repeat, how far and deep is the exclusion zone if future services are laid too close to the wall?
Daren? Do you want me to answer this question?
I thought you were going to answer.
Okay.
Oh, yeah, I would like you to, because you've come across this many times.
Okay. The job that I had my presentation about, the Oakdale West Industrial, that had a no-fines concrete on the top of the wall for 1 metre, and then straight after that no-fines concrete area, that's a free no geogrid zone. So that's pretty much dedicated for the services to be installed later on. I've seen services being very close to the back of the block installed, stormwater in particular, or other services. But I guess with this type of walls, you can always accommodate service, whether going parallel to the wall or perpendicular or an angle. You can accommodate that in your design by amending the design, the geogrid location or strength or lengths.
Cool. Thank you. Thanks, Namir. That person had another question, and it was how to account for the lateral force due to wind onto the wall in the example.
Well, yeah, sure.
Sorry. You go ahead.
So, of course, we need to look at wind loadings when putting fences or screens on top of the wall. As Namir said, we can put posts directly into the top of the block, and that is a benefit of Keystone, that especially for lot lining in between properties, we can put the fence directly on top of the block, whereas a lot of other segmental retaining walls, you need to put the fence post in the drainage area. when we're looking at larger wind walls or with loading, we need to reinforce it with concrete, of course. Be careful not to make the mistake of reinforcing just around each post, because what actually happens is if you do get some movement, you will see the top of the wall will wave and you'll get some bending. So you need to reinforce it with a larger concrete post at the back. So not just wind loading, but crash barriers as well. We have detail for all that. The projects use a lot on highways and larger infrastructure, so we need to look at vehicle crash barriers. So we have all those details, and usually it's a matter of coming back further behind the wall and putting stabilising the area with enough concrete or whatever needs to be put in place.
I add to this what Daren was saying. There is the federal highway in the US have a minimum distance from the top of the wall, the back of the wall, to the nearest post or being a sound wall or crash barrier, to be a 4 feet, 1.2 meters. 1.2 meters, that's the minimum, where if that is the case, there will be very minimal effect of that barrier onto the wall structure. And we actually looked at that in our Oakdale West project, and we considered that as well as but we still had to reinforce the post liners as you saw in the presentation.
Thanks, Namir. We have another question which has come through on registration, and that's from Eliza in Victoria. So thank you for everyone who actually posted their questions when they registered for tonight's event. Now, Eliza's question, and I might pose this one to you, Namir. What's the best retaining wall design or material for a sandy soil?
Sandy soils are normally good soils to work with in retaining walls. So being the retained soil, sandy soils offer free draining or less water pressure built up behind the retaining wall, and they are good materials to be retained. We actually use sandstone, crushed sandstone, which is a sandy material, obviously, as our main backfill reinforced material, backfill and reinforced zone material, most of our walls. So this is how, because it is a good material, it can be compacted, it's granular, doesn't have any expansive soil or any problems really using them. And they are available in the Australian market. So this is where in summary, sand soils are good soils to be retained.
Excellent, thanks, Namir. Got another question here, and this one's from Hasib from New South Wales. What are cost-saving alternatives to core-filled walls on piers where the client wants to minimise easements behind the wall and maximise usable area? Namir, did you want to answer that one?
Sure, and thanks, Hasib. I know Hasib, and it's a good question, actually. He's referring to a project where we've tendered for as UCBC. And you see, with Keystone retaining walls, having these the versatility in choosing between different designs and alternative options, you can always come up with something that's cost effective. With this case here, we looked at the no fines concrete as being the most cost effective alternative to the masonry walls sitting on piles. And we still think that this is going to be a good option for the clients, saving not only money but also time and effort. For us, this is really pretty much the best option we can offer.
Excellent. Mm-hmm. Daren, you didn't want to add anything there? All good?
Good, thanks.
We had a question come through, and we are coming to the end. So this one, a question from Liam. He asked, may I ask either speaker about soil erosion resistance over the long term? And have you ever constructed curved walls in elevation?
That's a good question. I don't completely understand the question about soil erosion resistance. I imagine that we would counter that by, in the reinforcing zone, making sure that we compact the materials, understand the materials, and compact the materials properly, particularly in the corners. And Liam also mentions a constructed curved wall in elevation, I'm imagining on grade. So that's quite normal for that to happen with segmental retaining walls. They won't finish dead. They will grade them back and normally curve them back. But just remember that with these types of walls, particularly the Keystone, it's best for everyone to build them as near vertical as possible. It makes it easier in the design and during construction. So curved walls aren't a problem. Grades aren't a problem. Curved walls on grades aren't a problem. But I'm sorry, I can't give much more information on erosion resistance of the soil.
Thank you. Namir, did you want to talk about any of the work that you've done? Have you done any work with the curved wall?
Yeah, curved walls are part of our day-to-day lives, actually. With curves, we find that using curves eliminates the corners, the sharp corners, and the walls look architecturally much more, acceptable, much nicer with curves, especially segmental blocks where you can actually create these curves, with the building these small segmental blocks. But just with the erosion control, I'm trying to think whether whether Liam meant the erosion of the top of the wall, the soil at the top of the wall, which we normally either have a capping clay layer to be used to cap the reinforced zone, or we have landscaping area or concrete, whatever surface that will protect the reinforced zone from water getting into it. So I'm not sure I understand the erosion question well, but I hope this might answer it.
Thank you. Well, look, I think we've come up to our last question. So I will pose this question because it's excellent, and it's from Miles. He's asked the question. He's in WA. Said, "Hi, I am a recent civil engineering graduate in Australia, WA. Would you have any advice on how to get started in the industry for an early career engineer?" Good question, I think. So, Namir, did you want to kick off with this one?
Well, to be honest, I find Australia has a lot to offer, and I don't know of any engineer that hasn't got a job. So really, just go out, knock on the doors, and I'm sure you'll find something. You'll find many opportunities. Australia is full of opportunities. So good luck, and I can help if you need any assistance. Let me know, and I'll try my best.
Yeah, and like in anything, any industry or discipline that you study in, networking, meeting the right people and going out to different industry bodies and government bodies and attending meetings such as Engineers Australia. The more people you meet, the more doors you open. Excellent.
Thank you. Thank you both. They were great answers. I think we've had a great Q&A tonight and great presentations. So I would like to, on behalf of Engineers Australia and our audience, thank you both. So a big thank you to Daren Gardner and Namir Asmaro for their time, their insights shared at tonight's presentation. Before we do finally go, I would also like to thank Austral Masonry, who has been our industry partner tonight, and their support for actually making this webinar possible. And finally, I would like to thank our audience. So a big thank you to you all for the questions which came through on the chat and through the actual questions of registration. Thank you. There's one last thing I would like to ask of our audience tonight. If you could please complete the feedback on the session tonight. That feedback, there is a survey which you'll find on the link below the screen. That feedback really will help us improve and plan for future sessions. So if you could complete that, it would be most appreciated. So once again, finally, thank you all for your attendance tonight and for joining us. And we look forward to seeing you at our next webinar. Thank you. Good night.